The accompanying graph shows titration curves for two monoprotic acids. Which curve is that of a strong acid? Well, strong acid, you get complete ionization, so you're going to start at a lower pH. So that's titration curve B. You're starting at a pH of 1 for titration curve B. And you're starting at a pH of 3 with titration curve A. So that'd be a weak acid. B, what is the approximate pH of the equivalence point of each titration? The pH at the equivalence point for a strong acid, strong base titration is 7. That's because you only have the autoionization of water. That's contributing H plus to the solution. Whereas with a weak acid, at the equivalence point, you got conjugate base, which hydrolyzes water to produce hydroxide, right, according to a KB expression. So the pH at the equivalence point for this weak acid was 8. Samples of nitric acid and acetic acid are shown here with a 0.1 molar solution of sodium hydroxide. Determine whether the following statements concerning these titrations are true or false. All right, so we've got 25 milliliters of strong acid, 25 milliliters of weak acid. A, the larger the volume of sodium, a larger volume of sodium hydroxide is needed to reach the equivalence point in a titration of nitric acid. That's false. The equivalence point is when you add the same amount of strong acid as, the same amount of strong base as acid. So that's going to be the same whether you're talking about a weak acid or strong acid. The pHs will just be different. B, the pH at the equivalence point for nitric acid will be lower than the pH at the equivalence point for acetic acid. That's true. At the equivalence point for acetic acid, you have acetate still in the water, which is going to produce hydroxide, according to a KB expression. C, phenolphthalein would be a suitable indicator for both titrations. That's true. Phenolphthalein has a wide enough range to incorporate both equivalence points for these titrations. All right, a 20 milliliter sample of 0.2 molar hydrobromic acid is titrated with 0.2 molar sodium hydroxide. All right, calculate the pH after the following volumes have been added. All right, so initially we're starting out with 15 milliliters of sodium hydroxide being added to the 20 milliliters of 0.2 molar hydrobromic acid. So the first thing, guys, is you've got to convert to moles of hydrobromic acid and moles of sodium hydroxide. This is an acid-base neutralization reaction. It goes to completion. All right, so bromide ion and sodium ion are spectators here. So moles of H plus moles of hydroxide equal mole equal water, right? So this goes all the way forward. In this case, the limiting reactant is going to be the hydroxide, and you're going to burn up all the hydroxide and be left with H plus ion. So with a strong acid, strong base titration, before the equivalence point, it's about the leftover H plus ion, right? H plus was in excess. Hydroxide was the limiting reactant, so just get the new volume. All right, you added 15 milliliters, you added 20 milliliters to 15 milliliters, so the new volume is 35 milliliters. So divide by 0.035 liters to get the molarity of the H plus. Take the negative log to get the pH. All right, I think I skipped over 19 and just went right to C, right, the equivalence point, where I'm adding the same amount of sodium hydroxide as hydrobromic acid. All right, so at this point, you're at the equivalence point, right? There is no limiting reactant. The base is enough to burn up all the acid, and all that's left in water is water, right? The autoionization of water is the only thing contributing H plus. So when you have a strong acid being titrated with a strong base, at the equivalence point, the pH is 7. What's the next? Did I do D? I guess they did D, right? So past the equivalence point, it's not going to be about the hydrobromic acid anymore. It's going to be about the leftover sodium hydroxide. So past the equivalence point, hydroxide is now in excess. So all of the the 4 times 10 to the minus 3 moles of H plus is burned up. That burns up 4 times 10 to the minus 3 moles of hydroxide. This is how many moles of hydroxide are left. Divide by the total volume, right? So 20 plus 20 milliliters plus 20.1 milliliters gives you 0.0401 liters. You divide that into moles, you can get the POH, and then subtract from 14 to get the pH. So that's titration with a strong acid with a strong base. It's about excess hydrobromic acid before the equivalence point. At the equivalence point, there is no more acid, so the pH is 7. Past the equivalence point, the hydroxide's in excess. All right, in this titration, we have a 35 milliliter sample of a 0.15 molar acetic acid, a weak acid. It's being titrated with 0.15 molar sodium hydroxide. Calculate the pH after the following volumes of base have been added. All right. So this is different than a strong acid, strong base titration. All right. And on the test and on the AP exam, almost always, you've got to be able to calculate what the pH is at 4 different points during the titration. At the very beginning, before any hydroxide's added, before the equivalence point, at the equivalence point, and past the equivalence point. All right, so there are 4 different problems. All right, so first off, we haven't added any hydroxide yet. So in order to figure out what the pH is before any hydroxide's added, it's a Ka problem. Now I put a titration curve up here to, again, note where the how the pH changes during this titration. All right, so it's a straight Ka problem, right? 0.15 molar acetic acid, you're losing X, making X amount of the conjugate base. You plug these concentrations into the law of mass action. Again, the initial concentration is presumed to not change significantly, and we solve for X. Take the negative log and get the pH. All right, so the pH before I've added any hydroxide is a Ka problem. All right. All right, so 17 milliliters of sodium hydroxide is added to the 35 milliliters of acetic acid. So the first thing you do is use the molarity and volumes to convert to moles of acetic acid and moles of hydroxide, and then it's a neutralization reaction. This goes to completion. Really, I should have only put in 1 arrow. We treat this like it goes to completion. So I look at what the limiting reactant is. In this case, it's hydroxide. So 2.55 times 10 to the minus 3 moles of hydroxide burns up that amount of acetic acid. And I'm left with this amount of moles of acetic acid and this amount of moles is conjugate base in the solution. This is a buffer. All right, so I can take moles of acetic acid, moles of acetate, plug into the Hasselbalch equation, along with the negative log of the Ka value, and solve for what the pH is. So before the equivalence point, we're dealing with a buffer. All right, at point D, we're adding 35 milliliters of sodium hydroxide. So I skipped C and went right to the equivalence point. So when I have 35 milliliters of sodium hydroxide added to the 35 milliliters of acetic acid, I have enough moles of hydroxide to burn up all the acetic acid. So we burn up the acetic acid and I convert to moles of acetate. So what's in the solution affecting the pH at this point? It's the acetate. So this is a Kb problem. What I need to know now is not moles of acetate, I need to know the concentration. So 35 milliliters plus 35 milliliters is 70 milliliters. I divide liters into moles to get the concentration of acetate, and it's a Kb problem. For every X amount of acetate I'm losing, I'm making X amount of water and X amount of hydroxide. To get the Kb value, I take the Ka of acetic acid and divide it into 10 to the minus 14 and solve for X. X is the hydroxide concentration, right? Not the H plus concentration. So take the negative log and get the pOH, subtract from 14 and get the pH. And notice at the equivalence point, the pH is not a pH of 7 with a weak acid. It's higher. It's because we have conjugate base floating around, affecting the pH, producing hydroxide. All right, so we're at the equivalence point. E, past the equivalence point. All right, so I've added enough. It's 35.5 milliliters, not 355 milliliters. We've added 35.5 milliliters of the hydroxide. So now acetic acid is the limiting reactant. So moles of acetic acid burn up, the 0.00525 moles of acetic acid, burn up that amount of hydroxide, and we'll have excess hydroxide. And that's the main thing that's affecting the pH, not the conjugate base at this point. That's going to contribute a minimal amount, especially with hydroxide floating around. So it's moles of hydroxide. What you need to do is get the total volume, divide the total volume in liters into moles to get the concentration of the hydroxide. Take the negative log and get the pOH, subtract from 14 and get the pH. And again, we get a big jump right past the equivalence point because there's no more acid in there to eat up the hydroxide. So, 4 different problems. A Ka problem to figure out the pH initially. We solve for a buffer until we get to the equivalence point. It's a Kb problem we get to the equivalence point. And then the last point, past the equivalence point, you're just solving for how much excess hydroxide is left and getting the concentration, getting the pOH and the pH. Explain the difference between solubility and solubility product constant. Solubility is how much of a insoluble solid will dissolve in water, whereas the solubility constant is the K value for how soluble that insoluble compound is. Now, a solubility constant only has one value at a given temperature, whereas the solubility can be infinite depending on whether you've got a common ion or not. So that's the difference. Write the expressions for the solubility product for the following ionic compounds. So we have insoluble manganese carbonate. So it's about the solid going into solution, right? For every mole of solid going to solution, you're making a mole of carbonate and a mole of manganese 2 ion. Solids don't appear in equilibrium expressions, so these are easier to solve for. If we're talking about mercury hydroxide, for every mole of mercury hydroxide, you're getting 2 moles of hydroxide and 1 mole of mercury 2. So again, concentration of the products raise the stoichiometric coefficients. Solids don't appear in the equilibrium expression.